Imagine stepping into a teleporter like in Star Trek. The machine hums, lights flash, and suddenly, you're gone. In the show, it's just a narrative trick. But in real-world physics, things get dark fast. Fiction skips the brutal detail. Your original body must be disassembled atom by atom. The Heisenberg uncertainty principle makes perfect scanning impossible, and quantum fidelity in real experiments only hits about 85%. That means any attempt to recreate you risks critical errors. Your memories, your personality, even your consciousness could be lost in translation. So, is the person who steps out really you, or just a flawed copy with scrambled thoughts? Let's break down why the science behind teleportation isn't just terrifying. It's a guaranteed nightmare for your identity. Teleportation's first real obstacle is atomic disassembly. Sci-fi makes it look easy. Step into a chamber, get scanned down to your atoms, and reappear somewhere new. But the laws of physics have other plans. The Heisenberg uncertainty principle means you can't measure a particle's exact position and momentum at the same time. The more you know about one, the less you know about the other. This isn't just a technical headache. It's a hard limit set by the universe itself. Your brain alone is a quantum labyrinth, packed with 86 billion neurons. Each synapse relies on quantum-level detail. To recreate you perfectly, a teleporter would have to map every single quantum state in your brain, a task the uncertainty principle makes fundamentally impossible. Even a tiny measurement error could have massive consequences. Neuroscience research shows that when quantum coherence breaks down, neural signaling gets disrupted. So if a teleportation scan misses just a few quantum details, your reassembled brain might lose key connections, memories, or even the ability to think clearly. Let's look at what happens in real experiments. In 1998, scientists managed to teleport the quantum state of a single photon. The result? An average fidelity of 0.80, meaning the teleported photon matched the original only 80% of the time. That's for one particle. Now scale that up to a human being, made of 10 to the power of 27 atoms. Even a 0.1% error rate becomes catastrophic. Your copy could arrive with scrambled DNA, missing neural pathways, or organs in the wrong place. And the original you, the machine has to destroy your body, atom by atom, just to attempt this imperfect scan. The technical hurdles keep stacking up. The amount of quantum data needed to describe every atom in your body far exceeds the capacity of any conceivable memory device by orders of magnitude. On top of that, your body's quantum states are constantly shifting. By the time the teleporter finishes scanning, the information is already outdated. Decoherence wipes out quantum states in milliseconds, so even the best machine couldn't keep up with the pace of change. Atomic teleportation isn't just a puzzle, it's a dead end. The process destroys the original, introduces unpredictable errors, and leaves no way to confirm that the copy is truly you. But if teleportation by disassembly is a nightmare, what about the sci-fi alternative, stepping through a shortcut in space itself? Wormholes have a reputation in science fiction as the ultimate shortcut, but physics turns them into something far more dangerous. Einstein's equations suggest these tunnels could connect distant points in space or time, but every step of the process is a death trap. The biggest problem? Stability. To keep a wormhole open, you'd need exotic matter, something with negative energy density. In the real world, the Casimir effect can produce tiny amounts of this, but it's nowhere near enough. On any practical scale, we have no way to stabilize a wormhole, so it would snap shut instantly and crush anything inside. Suppose you somehow managed to hold a wormhole open. The next threat is tidal forces. The throat of a solar mass wormhole would be just a few kilometers wide, far smaller than any human scale. As you approach, gravity would pull your body apart with brutal force. Your feet and head would experience millions of times more gravitational pull than your center. The result? Spaghettification. Your body would stretch into a thin strand, molecules ripped apart long before you ever glimpsed the other side. But the hazards don't stop there. Quantum effects near the wormhole's throat unleash intense radiation. Semi-classical calculations show that vacuum fluctuations and blue-shifted energy would bombard anything passing through with lethal doses of gamma rays. Even if you could survive the stretching, you'd be cooked by radiation in a fraction of a second. The energy unleashed here isn't something you can shield against. No material we know comes close to surviving this kind of onslaught. There's also the problem of where you'd end up. Theoretical models offer no way to control your exit point. You could emerge in deep space, inside a star, or next to a black hole, places you're not likely to survive for long. Every variable is unpredictable, from the environment on the other side to the exact conditions at the exit. Even the act of entering a wormhole could trigger its collapse, erasing any hope of a safe journey. So even if you could build a wormhole, stabilize it, and somehow shield yourself, the laws of physics still turn it into a cosmic meat grinder. The best-case scenario, you're obliterated by tidal forces or radiation. But let's say against all odds, you survive the crossing. The nightmare isn't over. Now you have to face the dangers of arrival. Arrival is where teleportation turns deadly in ways sci-fi barely hints at. The reassembly process demands absolute precision. There's no margin for error. Materialize inside solid matter or misaligned, fusing with the wall or your own lungs, and you're finished. The precision needed isn't just beyond current technology. It's beyond what's been achieved in any experiment with more than a few atoms. Quantum teleportation with photons requires nanometer alignment. Scale that up to billions of atoms in a human body, and the odds of perfect reassembly drop to zero. The environment at your destination is another killer. Air molecules already fill the space where you're supposed to appear. If the teleporter doesn't perfectly displace every atom of oxygen and nitrogen, you end up merged with the air, lungs packed with solid matter, bloodstreams tangled with foreign particles. Even in a vacuum, no experiment has ever kept a complex molecule coherent long enough for full reassembly. Maintaining quantum coherence for a human body is impossible with what we know. Now add the planet's motion. Earth spins at about 1,000 miles per hour at the equator. Even a millisecond time lag misplaces you by hundreds of feet at Earth's rotation speed. Impossible to correct in real time. Miss the mark, and you could materialize partially underground, or with enough momentum to be fatally slammed against your surroundings. Temperature can kill you before you even realize it. Your body needs to match the exact thermal state of the environment. Arrive a degree too hot or cold, and your organs could fail instantly. Achieving that level of thermal precision, atom by atom, is far beyond any energy source or control system we can build. No classical computer can solve these alignment calculations fast enough. The quantum state of a human decoheres in milliseconds, while the data and precision needed dwarf anything our technology can handle. The result? If anything goes wrong, neural collapse happens too quickly for you to even know if you survived. Teleportation's arrival phase isn't just a technical challenge, it's a fatal risk built into the laws of physics themselves. But even if you could somehow survive the journey and land in one piece, you're left facing the deepest problem of all: what actually wakes up on the other side? This is where quantum teleportation hits its most unsettling wall: the Copy Conundrum. The process doesn't move you. It scans and destroys the original, then reconstructs a new version from scratch. Quantum teleportation works by entangling your particles with a reference, measuring their states, and sending the information to the destination. But quantum rules don't allow perfect duplication. The no-cloning theorem guarantees that every teleporter run wipes out the original quantum state. So there's never a true copy, just a one-way transfer with total erasure at the start. Think about the ship of Theseus, but on fast forward. If every atom in your brain is replaced all at once, is the result still you? In teleportation, there's no gradual change. Your entire quantum blueprint is ripped apart and rebuilt elsewhere. The sense of self, built from entangled quantum states among billions of neurons, doesn't survive the scan. The new version wakes up with your memories and personality, convinced it's you. But there's no continuity, no unbroken stream tying the original to the copy. The quantum teleportation protocol doesn't just swap out hardware. The act of measuring and transmitting your quantum states obliterates the original. Every time the original is gone, The new body is assembled from local matter, arranged to match the transmitted quantum data. But that data set is enormous, mapping the quantum state of a human being with 10 to the power of 27 atoms would require more storage than any technology can provide. Even if you could record it, quantum states for something as complex as a human collapse in milliseconds when exposed to the environment. Decoherence destroys the delicate entanglement that gives rise to your consciousness, long before the process could finish. Here's the punchline. Every teleporter run is a biological kill switch, yielding a convincing imposter with no continuing self. The original ends. There's no way to know if the new you is truly you, or just a copy starting from scratch. The paradox isn't just philosophical, it's written into the quantum rules themselves. Scientists have teleported photons, tiny particles of light, over impressive distances in the lab. But if teleporting a single photon is hard, what happens when you try to scale up to a human? Here's the real difference between teleporting photons and teleporting people. Photons are simple, isolated, and easy to control. Scientists can keep a single photon suspended in a vacuum, perfectly shielded from the outside world, and use quantum entanglement to transfer its state from one place to another. The entire experiment is built around eliminating every possible source of interference. That's why we can teleport photons, or at most, a handful of atoms, across a lab bench. Now try to apply that to a person. Your body isn't a lone particle floating in a vacuum. It's a tangled web of 10 to the power of 27 atoms, all interacting, vibrating, and bombarding each other with quantum noise. Decoherence hits instantly. In a real environment, the quantum states holding your body together get scrambled in milliseconds. No practical material or shielding can prevent this. Experiments show even small molecules lose coherence almost immediately. The challenge isn't just about scale, it's about the fundamental limits of physics. Data storage is another brick wall. To capture the quantum state of a single photon, you need a tiny bit of information. For a human, the data load explodes, more than the number of atoms in the observable universe. There's no physical storage medium, real or hypothetical, that could ever hold this information. And even if you could somehow record it all, you'd have to process and transmit that data before decoherence wipes it out. That's not just a technical problem, it's an absolute barrier. Then there's energy. Moving a single electron's quantum state already takes measurable power. Replicating every quantum detail in a human body would require energy on a scale that could vaporize a city. The demands aren't just extreme, they're impossible with any technology that could ever exist. And the quantum rules don't let you cheat. Quantum teleportation moves states, not matter. The original vanishes, only a new bundle of quantum bits appear at the destination. Every protocol destroys the source. There's no loophole, no workaround, just a one-way trip with no return. So when sci-fi promises you a teleporter, it's ignoring the universe's most unbreakable rules. The laws of physics aren't just inconvenient, they're designed to stop exactly this kind of shortcut. And that's not just a technicality. It's a hard line that even the wildest imagination can't cross. Here's the bottom line. Quantum uncertainty blocks perfect scans. Exotic matter and tidal forces make wormholes lethal. Teleportation destroys the original and rebuilds a copy. No continuous self, just a new version with your memories. Teleportation isn't just dangerous, it's impossible under the laws of physics as we know them. The dream of stepping into a machine and reappearing somewhere else runs straight into the universe's deepest safeguards. Let us know your wildest teleportation questions below. If you found this mind-bending, subscribe for more reality checks.